this lecture I'm going to give is, in a sense, a discussion of some of the interesting number theoretical properties of string theory amplitudes. So string theory is, as you know, a theory that is a theory of vibrating strings, and it has as a limit quantum field theory. And the reason why I'm going to talk about string theory and not quantum field theory is because it gives you a setup to understand some of the properties that people have noticed in quantum field theory. And I will give you a motivating example coming from quantum field theory, real physical world. But for setting up a formalism, mathematical formalism, although I'm not a mathematician, that, explains where the specific properties arise. I will be working in the context of a string theory amplitude at genus 0, and I will talk about the special numbers that come from genus 0 amplitude. And at the end of this lecture, I will mention something about genus 1 and modular forms. But the story is much less well developed at genus 1, so I will spend much of my time about genus 0 amplitude. So, in fact, suppose you, as a motivation, suppose you want to compute a quantity that is called the anomalous magnetic moment of the electron. Okay, so this is a physical quantity that has been looked at from the very beginning of the history of quantum field theory. Schwinger, Dirac computed it, and so essentially you have to compute some kind of amplitude. I'm not going into the detail of what they are. Where you have an electron, and here you emit a photon. Okay, and you have a certain number of perturbative contributions. And this is organized in a series expansion, which is called G minus 2, the difference to the classical value, that is 2. This is what you compute perturbative expansion. And then you have a small parameter that you call alpha, which is this is the famous 1/37, which is the square of the charge of the electron. H bar is the Planck constant, and c is the speed of light. And then you have a perturbation in alpha over pi square. And then there are numbers here, pi cube, etc. Okay. So the first number you get here is 1/2. Then here you get a number which value numerically is -3 to 8. Okay. Then there is a number which value, so it is an alternating series, 1, 118, etc., etc. So if you evaluate them analytically, you find that this number here turns to be some rational number, pi square over 12 minus pi square log 2 over 12 plus 3/4 zeta of 3. Okay, so that's for this number. Yeah. And the one here is, so here I'm not going to write the coefficient. So it's a linear, so here you have a pi square, and a log 2, you have a zeta 3, and the coefficients are rational numbers. Okay, so I'm not going to write the rational numbers, I'm just going to write the transcendentals. So you have pi to the 4th, you have some pi square, you have some pi square log 2, because here the list is much longer. There is zeta 3, there is some pi square zeta 3, there is some zeta 5, and there is something that is Li4 1/2. I will what? It's too small. Okay. Li for 1/2 plus log 2 to the 4th minus pi square log 2 square divided by 24. Okay. Etc. So you see that they are very with rational coefficients, and they are very special numbers. So you see here, you see pi, you see log 2, you see a quantity that is called zeta free, is the value of the Riemann zeta. So this is zeta of n, zeta of s, n to the s, okay, for s equal 3. And there is a guy that is Li4, 1/2, yes, which is some. So this is the value of, for z equal 1/2 of Li4 of z, sum n square n to the 4th, z to the n, okay? And the thing is that, and of course, then the question is that, what are the other quantities? So they have been computed analytically. So there are computations up to 5 loops and 12,000 diagrams. I mean, it's a complicated computation in perturbation. Lot of integrals to compute. But at the end of the day, you notice that there are very specific numbers that come in with specific, there are numbers that are present and numbers that are not present. And they come into very, very particular combinations. And the idea is to try to understand what is very special about these numbers that you meet in quantum field theory. And so the one thing that people noticed is that if you give a notion of a weight, and then, okay, later on I will precise this notion, but this is, so first you decide that you give a quantity that you call a weight to quantity that anything that is log or pi, you say it's weight 1. Then you realize, by looking at the computation that is done there, that at order L, order alpha over pi to the L. So it's important actually that you normalize your computation with a pi here, with alpha. We will see that pi has to be as well put together in a right way when I will discuss genus 1 amplitude in string theory, that you get quantity that have a weight only up to L minus 1. So I hope I did it right. So no, 2L minus 1. Sorry, 2L minus 1. Yes. And okay, so you see that there is a bond on. Okay, I'm sorry, I didn't say the weight of zeta n is n, and the weight of Li n. Excuse me? Yes, n can be 1. I mean, because it's so for n bigger than 2 in that case. Okay. Let's do it like that. So for z equal 1, this Li4 of 1 is going to give you the same as if I have, you see, if I decide that I have Lin of z, Lir of z is sum n bigger than 1, n to the r, z to the n. Okay, so the value at z equal 1 of this polylog is the zeta value that is here. So this one weight n, right? So
is the x that you have in
x.
Log of x. Log of it.
So it's a function. It's a function of z. So I'm looking at the. Who is asking the question?
What is the weight of log square?
2.
So the weight is additive.
The weight is additive. Okay. So the weight is additive. The weight of log n log, okay, log z to the n is n, and the weight of pi to the n is n, okay? So you experimentally notice that there's a relation between the maximal weight you get at a given order in perturbation and that the weight is bounded by 2L minus 1 if L is the order in perturbation, okay? But then you notice that here, so there are log 2s, there are log 2 square, but there's no log 2 cube. Yes?
So do you suppose that weight of alpha is equal to what?
2L minus 1. Yes.
Of alpha?
The weight of alpha. No, alpha is my expansion parameter. Okay. So if you want that, okay, that's a good point. If you want that this quantity has no weight, I mean, then you can try to put a weight to alpha to the pi. But I'm not pretending I'm doing that, no. Okay? It's just a bookkeeping parameter.
Yes. So did you claim that at any order you get only linear combination, polynomials with rational coefficients of this quantity which you wrote?
No. No. Up to the computation that I've written, yes, that's true. At the next order, there are over integrals that are polylog type, but there are as well elliptic integrals. But the question is that how can we understand the systematics of what's going on at higher loop order, knowing that this result comes by computing very complicated values of integrals, and then what is the rule that make the result much simpler than the way it was computed? And the question is that what happens at higher orders, okay? So the thing is that you see that there seem to be some simple rules, but as well you notice that there are missing terms if you decide that the weight is just the rule that you want to assign to the result. So the question is that what could be the organizing principle behind that? So the organizing principle behind that actually has to do with so this is perturbative quantum field theory. So there is a relation between that and the notion of motivic period and motivic Galois theory. I mean, started with Grothendieck and Pierre Deligne, but essentially there is the notion of the motivic Galois group that Pierre Cartier introduced and then was later, developed more by Francis Braun, that tells you how there is an mathematical organizing principle that help you to understand, the systematics of the numbers that you meet in quantum field theory. So the thing is that there are class of integrals that gives you objects that are zeta values. Zeta values are numbers that are polylog. Polylog is a function. This polylog evaluates at 1 to a zeta value. So this is, in fact, if you understand this function as that function of R as a function of Z in the complex plane, you understand something about its special value when Z equals 1, okay? So in general, when you look at a result and you look at numbers, it's very difficult to get some generic properties about numbers. It's easier to get properties about functions. Okay, so that's the main idea. Is that the point is that you want to understand what are the properties of functions, and you want to build functions that in fact cover. So I want to discuss functions that actually cover the numbers that you see here. That means the zeta values, the polylog, and their generalization. So the multiple zeta values and the multiple polylogs. And some of them with different analytic properties in the complex plane, and that will be why I will have to discuss the genus zero amplitude in string theory, as they are generators of all these numbers. So some of you may already been exposed to some of this discussion by Francis Braun, for example, because he's one of the main contributors to the mathematics of that, or our string theory colleagues. So I'm going to give you a way to think about that looking forward, a generalization of the argument not just to integral that have to do with genus 0 period, not only to period on the Riemann sphere, but as well to higher genus order.
By the way, I think the question of Nuno was log of pi. Would it ever appear?
Log of pi?
Yeah, just to.
Log of pi.
Zeta, saying an argument in the complex plane.
Okay, I can look at the valuation of this polylog at any values in the any complex values, right? I can even look at the polylog at root of root of unities and things like that. Then the point is that the argument, if you have log of pi, that's a good question. So what is the transitivity weight of log of pi?
It never appears.
No, it never appears in quantum field theory. So in a sense, this is one particularity as well. Maybe that's a good point as well.
Plenty of numbers you don't expect to appear.
Yes, so that's
Here is that you expect sort of multi-zeta values, but you do not expect log of pi.
Yes, you don't expect log of pi. You don't expect, but you can have quantities that are polylogized with here root of unities, if you want. In quantum field theory as well. So that gives you other set of numbers. So in the class of numbers that you generate by evaluating your function at special point, is kind of large. So what you want is that you want to discuss the notion of weight associated with the function, and then look at its special values and what happens for the special values.
But you presumably only allowed to evaluate them at algebraic points or something.
In a sense,
I'm trying to say what is a period? Isn't that
I'm trying to say what is the period with. I'm trying to say what is the period without doing the theory of periods. But I want to say as well that in quantum field theory, for some reason, there are periods that appear and periods that don't appear. And that's the big question. Because you can think about evaluating your quantity to, concerning, value of II4 of pi, and why it doesn't appear. So what is the organizing principle?
So is that working for phi4, standard phi4?
Yes, for phi to the fourth, there are explicit results for which number you get from in perturbative expansion, and this is the starting point of all the field in a way. When Broderst and Kramer, they did all their perturbative computation in phi4 and phi cube to very high loop order. They used the result of our colleagues in mathematics and comparing what is known about the generalized, the multiple zeta values that I will introduce in a minute. And then people started to build a data mine. So a huge databases of special number that appears in quantum field theory. So suppose you have here a very good numerical evaluation of your result. So you have done numerically, but you don't know what is the analytic expression. But you know that, my result has only up to weight 3, and it can only contain zeta 3, pi square, log 2, and pi square, And you don't know the coefficient here. So what you do is that you can use an algorithm to really, from high accuracy determination of the digit, that number, determine the rational coefficient here, And you can do it as well at this level, except that then you have, so these zetas, pi's, logs too, maybe they are not so exotic, but then you have to realize that you have to introduce some polylog evaluated at 1/2. So this is more complicated. But if you believe you have a good databases of transcendental of numbers that you can fit, you can use this PSQL algorithm to determine the rational coefficients, Because here, as I said, it's rational coefficient, So in a sense, physicists were using that until more powerful theorem by Francis Brown in particular came out to clean up the scene and give a more mathematical basis to all these considerations. So since quantum field theory is I mean, very diverse. I mean, I'm going to switch to genus 0 string amplitude because this is where I will be able to discuss the properties of these numbers, the polylog and the zetas. So I'm not going to use a lot of string theory. So it's not a course on string theory. So I'm just going to make a statement. So genus 0 string theory amplitude come into two families. Okay. So there are the closed strings and the open string. Okay. So closed string means that I have here the Riemann sphere. You have some mark point on the sphere. And here you have, for example, the disk. Okay. So this is a disk. And you can have point on the boundary of the disk, but you can have point as well in the interior of the disk. Okay? And the claim, which I'm not going to explain, is that what you call the closed string amplitude is some finite linear combination of building block amplitude. Okay, so I'm going to call that M. So here, if I have n point here, I'm going to give you, call that n. That depends on some physical parameters that I call s, some integer. And here I have some coefficient that depends on s, some integer. Yes, I will. Okay. I will write bigger. Okay. Okay. And the open string amplitude is sum over sum. So in a sense, I mean, I'm just here, it's a finite, there's a finite number of terms here. So I don't have to, and then there is what I call an of s and n. Ah, okay. Okay. So, and the fact is that the number that I've described here, the zeta values and their multiple zeta generalization, the polylog and the multiple polylog version, they arise from integral you compute by integrating over the sphere or having integrals over on the disk with vertex operators in the boundary or in the bulk. Yes, yes, but this is what I'm saying. Yeah, this is what I'm writing it. So this is what I call the building block. This is the only thing I want to building blocks. And this is what I call the other building blocks. Okay, and the interesting number theory comes into these building blocks. These coefficients are just rational coefficients in terms of the kinematical variables. And it's a fact, I'm not going to explain it, there is no number theory here. So in a sense, this coefficient, there is no pi's, no zetas, no, just a rational function. It's a rational function, okay? The same here. So your physical amplitude is this. This is a combination, finite combination of something that contains the interesting number theory. Very good. I'm going to tell what. Yes, I'm going to tell you. Yes. Okay, so what is now the building block? So M, N. Okay, so I'm going to call that N plus 3 is integral. Is it so on so this is Jeremy will answer your question. N plus 2 of so let me make 0 because it's a genus 0 times. So the formula continues. sorry, it's not Z, it's W in my notes. And then I have this complex conjugate here. J, yes, and I'm integrating over, so to y pi, okay? Okay, so that everybody can read. So the thing is that I'm going to give you, to tell you what is this g in a minute. So this is an integral over, so here I have a label that has n plus 3. I'm integrating over 3 variables. It's because you, by the symmetries, the two symmetries on the sphere, you can fix 3 points. And by convention, I always decide that I fix 3 integration variables to, they can be fixed to anything, to any constant. So I decide to fix them to 0, 1, infinity, because you see the function here, Lin of z, as you know, it has a branch cut that starts at 1. Okay, so I like to have the 1 here. Yeah, I'm integrating over n points of a quantity that is the exponential of 2 alpha prime Sij g of wi minus wj, then the derivative of that function to the power minus 2 nij, and the anti-derivative to the power n bar nij. So I have alpha prime will be my expansion parameter. So it's a positive, real positive parameter. It will play the role of the alpha over pi over there. Sij are complex parameters. Okay. Nij and Nij bar are integers. They don't have to be positive. They can be positive or negative integers. Okay, but I still haven't given you the most important information. What is G? Okay, so Jz z bar is minus 1/2 log z minus z bar. Okay, z minus z. No, z prime is z minus z prime square, which is minus log z minus z prime plus log z bar minus z prime bar. Okay? So this guy is the modulus square of the difference of the, did I put a comma or a minus? Okay, of the argument. What? Yes. Thank you. Okay. Very good. So now there is an integral that is like that. Okay. Now this computation here, I have to define what is A. A is defined the same way, if you want. So A n plus 3 is, so I'm not going to write a precise integral because I will write a precise integral in a minute, but I want to explain you something important. So A is the same, but you will see why I will call same, as the closed string amplitude, but with the function g that I call in that case disk of z prime, that is defined to be minus 1/2 Okay, so I hope you can read. So here's that part here is the same as this one. So this is the log of the modulus square of z minus z prime. But this part is the log of the modulus square where z is z bar. So there is z minus z prime as z bar minus z prime. Okay? And why is this like that? And that's a very important point in all the construction is that. So what you see is that the disk, if I have two disks, okay, I'm not drawing, okay. I should have practiced my drawing before. Okay. So let me make a sphere, and if I cut my sphere in half, okay. So the double covering of my disk, I mean, if I put my two disks together, I get the sphere. Or if you want, if I have a sphere, and if I have an involution, I of z, that is z going to z bar, then under the action of the involution, the disk is the Riemann sphere divided by this involution, I disk. Okay? Now, by construction, when you define a quantity on your, so if you have your Riemann surface with a boundary, or as well, if you have a different involution, you can have cross cap. If you define what you call the grain function on that object, you get it from, you get this quantity G is the grain function. The grain function on the disk is obtained from the grain function on the sphere by applying the action of the involution. Okay, so this is 1/2 G0 I Z. No, d'abord, first I have the identity I Z Z bar, and then I apply the involution on the first argument. Then I apply the involution on the second argument, and then I have the involution applying on both arguments. Okay.
What are the boundary conditions for the grain function?
Ah, no, it's closed.
No, on the disk.
So I'm telling you that I'm giving you that quantity here. Okay, so the second derivative with respect to z is the delta function. Okay, you define on the sphere. And now I apply the involution, and then of course I'm going to get you an object that when it will be actually the quantity I have to use in equivalent formula for my amplitude on the open string once I have applied the involution. Okay, so if you apply a different involution, which is the I z minus 1 over z bar, you get the real projective plane, okay, which I'm not going to discuss, but it's very similar. So that's another open surface, and it's a descendant of the closed string case. Okay? Yes?
This function you wrote below is the disk one, right? Not GM.
This one? So this one is disk. Yes, yes. If you have another involution, then you apply the same formula. You apply the involution here. A genus one, that will be the same. Okay, so that's the construction. Okay.
You have 4 terms here, but
yes.
in your definition you only have 2.
Yes, because if I apply it, so this one is the complex conjugate and complex conjugate, and I have the modulus square. So this term and this term, okay, I will do it in front of you, hopefully, up to factor of 2. Yes, so I have minus 1/2, and I have log of z minus z prime square, so that's the first term. So the last term I apply the involution is z bar minus z prime bar modulus square. But because this is the complex conjugate and this is the norm square, this guy is the same as that guy. Okay? And this one is log of z bar minus z prime square plus log of z minus z bar square. And this one is the same as this one because the modulus square of...
So my point is that there is probably just a factor of 2 in front.
And there's an extra factor of 2 here.
Yeah, but it's already in your list.
No, no. So there is the factor of 2 of the green function. This guy is equal to this guy, and this guy is equal to this guy. So this is twice. So there are 4 terms that twice 2 terms that kills the factor of 2 that is here. Okay. So normally this is correct. Okay. Excellent. So now what's happening is that, now that I have done that, I can write an expression here. So yes, maybe I will do this like that. Where's the stick? Okay. Okay. I need to present this because you will understand in a minute why I'm spending some time on this. So what's happening is that so I want to write what is an plus 3. Donc, I put disk so that everything is clear. And what I want to do is that I want to, because of lack of time, I want to restrict myself to the case where it's a disk. I have just point on the boundary. So the boundary is the fixed point of the involution. Okay. So this disk, I map it. It's mapped to the parallel plane. Okay. So then I have here a parallel plane. If you want, this is infinity. This is 0. And this is minus infinity, okay? So that means the amplitude that are with point on the boundary, that are on the fixed point of the involution, there will be integrals where I'm integrating with point on the real line. This is the real line. Okay. And so I'm going to get some integral of so essentially what I do is that I apply this with now here the point that are on the real line, so that means the green function between x and x prime. So I apply z equal x and z prime equal x prime being real. It's minus 1/2 and it's log of x minus x prime. This term and this term give the same, so this is 2, 2. This is minus log. Wait a minute. Yes, minus 2 log of absolute value of x minus x prime. Okay. Okay. So the 2 term gives the 2, and then the 2. Yeah. Okay. So essentially, I'm getting the log of the absolute value of the difference between the point. Okay. So the thing is that what you have to consider are class of integrals where. So if I expand, now I have exponential alpha prime, the log of the difference of the. So I can write the term as product ij and 1 xi minus xj. Okay, so 4 minus 4, and then I will have sij, and then I will have here things that are absolute value of xi. I'm sorry. Yes, minus alpha prime. No, minus. Yes, ni puissance ni. What do I have? I had a 2, I have a 4, and there's a minus 4 somewhere, right? Something like that. And then I have. Yeah, I have difference. Yes, I'm sorry. Yes, yes, right. It's xi minus xj. Yes, this is why I was getting confused. Xj minus 4 nij. So I have an expression like that, of product from 1 to n point. Okay? Now, n plus 3. So this is, no, what the point is that here over there, what I had is that I had fixed 3.1 to 0, 1, infinity. 0 and 1 are on the real line. So that means I'm getting an integral, class of integrals that are like that. And if I use the fact that I have fixed 3.210 infinity, I have product from 1 to n, absolute value of xi minus 4 alpha prime s I n plus 1. Then I have 1 minus xi minus 4 alpha prime s I n plus 2. And then I have the factors with the integers, which is xi n I, 1 minus n plus 1, xi n plus 2. Yes, I will write bigger. Okay, very good. So now the thing is that I want to understand this property.
Change n plus 3 to n on the left hand side, right?
Yes, I'm sorry. Yes. Okay. So I want to understand now what are you want to understand what is the small alpha prime expansion of this expression compared to the property of the small alpha prime expansion of that integral. Okay? So what's going to happen? So I'm telling you because a lot of you already know what's going to happen, is that this one will generate all the zeta values, the zeta free and their generalization, the multiple zetas.
When you get expansion, it still depends on Sij. You get
Yes,
like product
yes.
of linear combination.
Yes, it's a linear combination. So the coefficient of the alpha prime expansion.
There will be some products of linear forms in Sij, and for each product of linear form gets multiple zetas.
Yes, that's right. And for the closed string, there will be a very specific subset that's called a single valued, and single valued will be defined. But the reason why I'm telling you that, and because for the people who know the story from Francis Brown construction, is that so what's happening is that the single valued projection is obtained by using the cancellation of the monodromies of the function of the complex plane. So you need to have a notion of complex conjugation when you do the single valued version of your polylog Li of z. And it turns that actually the single valued projection, and this is what I want to explain in the genus 0 case, is that the single value projection is kind of an inverse to the involution. So in a sense, you build the open string going from genus 0 closed string amplitude. You apply an involution, you go to the disk amplitude, and the single value projection goes the other way. So this is what I want to show it to you, not in the general case, but in the specific case of the 4-point amplitude, for example. Okay. 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 So now let me do it like that. Okay. So one example. So now I'm getting very concrete. And since I explain where I want to go, maybe that will help to see. So let me take an example of the, so this is my disk, and I have 4 points. So n plus 3 is 4. So that means in that case, I have just an integral, a, that is 0 to 1. Let me consider that integral, minus 4 alpha prime. So S12 alpha prime minus 4, that's going to be S13 dx. So this is a non-function. This is a Euler beta function. So it gives you 1 over gamma 4 alpha prime S12, gamma 1 4 alpha prime S13, divided by 2 minus 4 alpha prime S12 minus 4 alpha prime S13. Okay? So now the claim is that all open string 4-point function this, so actually I want to call it V because it's Veneziano type of amplitude, are going to be a rational function of alpha prime S12, alpha prime S13, rational function times V. So I'm not going to explain that. I mean, you can look in the paper I wrote with Federico Zerbini for an explanation of that. So the thing is that all the 4-point amplitude that you can think in string theory, that means the disk, we all point on the boundary, point in the bulk, point on the boundary, or on the projective, the RP2, amplitude on RP2. I'm not sure how to, well, I can draw a cross cap if you want. Up to a rational factor, it's a rational factor. So when alpha prime will be small, this will have poles, but there is no pi's, there is no zeta values, times the function that is this ratio of gamma function. Okay. So now I want to do the alpha prime expansion of that. Okay. So I use that gamma of x is exponential Euler gamma constant times sum exponential of sum m bigger than 2 zeta m divided by m of minus x to the m. Okay. So that means, I mean, if I plug that thing for each of the gamma factor, now you see that this plus this minus this is 0. So the Euler gamma constant is going to disappear. And you are just going to keep something that is some power of alpha prime and the kinematics times the zeta values. So that means you have an expansion that is 1 minus sum ij bigger than 1 alpha prime S12, I'm sorry, alpha prime S12 to the I, alpha prime S13 to the j, Pij, where Pij is a polynomial in the zeta n, the zeta values, where of weight I plus j, yes. Because here you see the index m, zeta m. So I told you that what I call weight of zeta m is m. This comes multiplied by alpha prime. So alpha prime goes with that. And if I have the weight, it's additive. So if I have zeta m, it's the weight m plus n. Okay, it's an additive property. Okay, very good. So this is something that people looked at. I mean, it's an exercise that you do. Now I want to obtain this expansion in a very specific way, that by expanding the integral directly. Okay, if I expand the integral, okay, so yes, so if I expand the integral for small, so I mean I'm sorry, I should have said, I'm putting myself in a region when the integral converges. Okay, so there is, if I can always choose the region in the complex plane for my complex variables S12 and S13, so that the integral is convergent. So I do a small an expansion of the integral, small alpha prime expansion
Sorry, Pierre, but for such kind of million transform, you don't really interested in convergence. It's meromorphic functions anyhow.
Yes, yes. Okay, so if I do that, then I'm getting something that is, okay, I mean, there is the trivial term that is 1, and then there is the term when I have alpha prime s to the I, s12 to the, I'm sorry, s12 to the I have log of x to the I divided by factorial I, 1 minus x to the j, factorial j, okay. It's bigger than, okay, well, 0, whatever. And then I have to, okay, I think I did, yes, I somewhat did something a little different on my note. Yes, okay, so maybe I will look at the integral that I have on my note, because that way I changed the notation when I wrote it. So what I will do is that I will look at the integral that is the integral between 0 to 1. Yes, this one is better because it will be x to the minus, and I will lose alpha x minus alpha prime u to the minus 1 dx. Okay, very good. And this one, again, it's up to a shift. I'll recall what it is. Prime u, 1 minus alpha prime u s alpha prime u. Okay. So what I do is that I do the small alpha prime expansion here. And so first, I have to treat the fact that there is potentially a pole when alpha prime goes to 0. So I just look at minus alpha prime u 1 minus x minus alpha prime u dx. And then I have the integral where I is bigger than 1, j bigger than 0. Alpha prime u, j plus 1. And then I have log of x to the I over factorial I. Yes. Log of 1 minus x factorial j to the j dx over 1 minus x. Okay. And then I have an integral between 0 to 1. Okay? So the first factor gives me 1. And then I have ij, sum over ij, alpha prime s to the I, alpha prime u to the j. And then I have a quantity that I call q, ij of 1. So this evaluates to a number. Okay. If you give it to Mathematica or any program or Panzer program that integrates this thing, will give you that it's a combination of zeta values. But this is not what I want to do. What I want to do is that I want to introduce a function, because this is the important point, which I call q of z, and this will be the value at z equal 1 of my function of log of x I, okay, factorial I, log of 1 minus zx to the j, factorial j, dx 1 minus zx. And so what's happening when I'm doing that is that this function turns actually to be a particular case of the function that is a multiple polylog. So if you evaluate it, this is what it's called a Nielsen polylog logarithm. It is given by 1 over z li 1 1 1 1 I plus 1, yes, I plus 1. Here I have j of them. I have 1 1 1 j z, where li, the r1 rd of z is sum z to the nd product I from 1 to d, the n d n I to the I, and then I order them so that I have so my ordering of the summation of my polylogs is, okay, just a minute, I have to look at my convention. It's the usual convention, but if I don't look in my note, yes. So Ri positive. Okay. So this is 1. So this is a function of z that when I evaluate it to 1, it gives you a generalization of the zeta value that is called the multiple zeta value. And this integral is an integral that you can evaluate. I mean, I don't have time to explain how you do that. And it gives you a multiple polylog. Okay? Of z. Yes?
Why do you have two variables in this line and only one in the...
I'm sorry. Yes. Good point. Yes, I'm sorry, because I forgot to write them. So Z1, Zd, yes, Zi and I. Yes, I'm sorry, yes. It has as many variables as I have indices, and this is the case where you have 1, 1, 1, 1, 1, Z. And the number of indices is number of variables, and the last entry is my Z, and the other one are 1. Okay, so this is this.
Is your function Q that it's one of integrals you just throws one vector?
Yes. So why I'm telling you that? Okay. So now, what's happening is that first, this is strange because if I evaluate this, okay, well, so let me do it like that, yes. So if I evaluate, yeah, maybe, okay. Well, maybe I want to keep that, and I will go there. So if I evaluate that object at 1, then I'm getting that the integral that is upstairs is 1 minus some ij. So alpha prime si, alpha prime u, I think j plus 1, of q ij of 1. But this is the li with all ones, which, so this is in fact sum. So I have here an object that is called zeta 1, 1, 1, 1, 1, I plus 1, where I have j of them, where zeta n1 and d is sum r1 rd is n1 and 2 and d product L from 1 to d 1 over nl rl. Okay. So on the other side, I mean, the expansion of the gamma function gave you immediately that it was a polynomial in the zeta values. And these numbers look like different.
Sorry, that's also different prime a prime u to power g plus 1, and here on the last go.
Okay, I messed up with the indices. Yeah, okay, so there is a shift maybe by 1 or plus 1. Okay, so I think it's plus 1. You don't see it because of my bad writing in the integral. Okay, so now if you look at this, then this is what I said, is that you have to understand what are these numbers. Okay, just a minute. I need to get my, yes. In fact, you look at them and then you look, what is zeta 1, 2? And in fact, this is zeta 3. That was known by Euler. And in fact, Euler knew that zeta 1, 3, I'm not going to write too many of them, but it's zeta 2 square over 10. So this is pi square over 6 square divided by 10. And zeta 1, 6, for example, is minus 2/5 zeta 3 zeta 2 square minus zeta 2, zeta 5. So this is weight 7. 5, 6, 7. Okay, that's good. Okay, so this is. So the fact is that if you massage this sum, Euler could show that this is only standard numbers that he knew the zeta values. In fact, I mean, there's a result by Hoffman that tells you that all this 111 entry actually generate the expansion of the gamma function, and actually this ratio of gamma function is the generating series for all these zetas. So that's something you can prove. Okay, excellent. So now of the beta function, yes, of the ratio of gamma function, which is the beta function, yes. So now what I want to look at is the other integral, which I have not kept, of course, which is now the integral on, so that I'm keeping, yes, which is the integral on the sphere. Okay, so the sphere integral in that case, so M sphere. Okay, let me write it for the case of 4, so that by lack of time, I mean, it sense, I mean, I need to. So if I apply n plus 3 equal 4 in the expression I gave before, I get some integral that is of that form. Yes, 2 alpha prime s 1 minus z minus 2 alpha prime s1 2 s1 3 z and 1 2 z bar and 1 2 bar and 1 3 and 1 3 1 minus z and 1 3 bar d2z. Okay, so you want to evaluate an integral like that is very similar to the one that is there, except that you integrate over the complex plane. You have the measure of integration is dz dz bar, and here you have the parameters, and it will be the same as this one with the integers here ni j to be 0. Okay, so I want now to look at this, and I want to do this computation. So as before, you see, the case there is that it was interesting for me to introduce a z value, a parameter. So what I'm going to do is that I define a function g of eta, which is an integral over the complex plane d2z of z of, and I'm going to generalize because this is why I'm going to the main point of all this exercise. Okay, so this integral here, or maybe I should write bigger, I suppose.
By the way, do you divide dz bar by some pi?
Yes, there is some. Yes, yes. So the important point is that, okay, so this integral is the same as that integral, where if I set eta equal 1, and I have some relation between, so I have a equal a bar equal alpha prime s1 2, and I have b plus c, b plus b bar equal alpha prime s1 3. Okay.
So you need something like a minus c bar should be integer, yeah, to be one day.
Maxime, this is exactly what I was going to say. Yes. So the thing is that the important point is that I need, indeed, that a minus a bar to be an integer, you know, b minus b bar to be an integer, and c minus c bar to be an integer. And why I'm doing that? I'm doing that because this function in the complex plane, eta plane, has, I want that it has very specific monodromy properties. So in fact, the quantity, the Q of Z over there is a polylog. So this polylog is a multi-valued function in a complex plane. It has a branch cut that starts from 1 to infinity. Okay. This quantity here, if you have the difference of the holomorphic and anti-holomorphic part that is an integer, it has no monodromies. And in fact, this is the whole point. This is the whole point that this is exactly what you know in physics, is that the conformal correlator is single-valued function of its parameter. Its expansion on conformal blocks. The conformal blocks are the open string amplitude are multi-valued. And the fact is that the expansion of the conformal correlator, that is a single-valued function on multi-valued function, gives you constraints on the expansion coefficient. And in fact, this is what the advertisement I said, is that here there is a bar, and so the complex conjugation. And it's exactly the complex conjugation that Francis Brown is using to make a single-valued projection at genus 0. And this is really, the single-valued projection is really the inverse operation to the conformal block decomposition when you do that at genus 0, and hopefully, well, we know it works at any genus order, but it's not so well developed at higher order. Okay, so now,
Sorry, could you explain again what
yeah, I'm going to explain. Yes, I'm going to write it. Yes. Okay, so now I want to compute that integral. So I'm going to use a method that is known to physicists due to Dotsenko FATF, and I was very lucky to have Vladimir Dotsenko as a teacher at the École Normale. So this is where I learned that, and I made a lot of good use of this. So what you do is that you want essentially to split that function a, b, c, a bar, b bar, c bar, eta, and you want to separate the z and the z bar integration. Okay? So if I just naively write just a minute, I'm looking at my note. Okay, so if I just write, yes, right, this is this. So if I write an integral that is za 1 minus z b eta minus z c dz, and here another integral that is z bar a bar 1 minus z bar b bar eta bar z bar c bar dz bar, and I don't, okay, then I have to specify the way I do that. I want to preserve the same analytic properties of the function when eta varies in the complex plane. So I need to have here some kind of a quantity that depends on a, b, c, a bar, b bar, c bar, that tell me that actually I have not screwed up with the monodromy properties of the function in the complex plane. So one way to do it is to do some change of variables to rediagonalize the z and the z bar and rotate the contour of integration. And so if you Dotsenko AF from 85, and in string theory this is known as a KLT. And KLT is the same, I think the same year. Okay, forgot. So you get at the end of the day that this function a, b, c, a bar, b bar, c bar, eta is given by okay, I over 2 pi, a matrix called G1, vector, okay, and then I have to look at my note here to see how this is written in the correct way. Okay, so where is my G1? that's not, of course, I don't have it here. Okay. Why did I write it? Okay, so this is 9, this. Sorry, I lost the page in the fight. Okay, so I lost the page. Okay, it's okay. So where do I have it? It's here. It's here. I see, it's here. There you go. I have it. So I have here a vector that is an integral between 1 to infinity. Yes, this is z. I have to write it bigger. So this is the integral from 1 to infinity, z to the a, z minus 1 to the b, z minus eta to the c, dz. And then I have an integral that is 0 to eta, z to the a, 1 minus z to the b, eta minus z to the c, dz. Here I have I call that one I1 of z, I1 of eta. So this one is the transpose. So this is the same integral. So this is let me write it like that. So it is transpose of I1 transpose eta. So this is a column vector, this is a line vector. In the middle, here I have a matrix that is okay, so it has 0, 0. It is sinus pi a sinus pi c divided by sinus pi a plus c. And here I have sinus pi a plus b plus c, sinus pi b, sinus pi a plus c, and there is a minus 2i, this 1 over pi. Yeah. Okay. So what's happening is that once if you compute that integral by separating the z and the z bar variables, what you find is that you get some linear combinations of two line integrals. So this is the two integrals where I essentially have z and z bar separated, but with a specific range of integration. So this is, so when I have separated the integral, I can project the z. I can decide that z is on the real line. So I have 1 to infinity. Here I have 0 to eta. And here I seem to have said that there is only one term. But in fact, what you get when you do it in general, you find that you have two terms. So this is this integrals times itself times this factor. This is a diagonal matrix. And this integrals times itself times this factor.
Eta is in upper half plane, or what is it?
Eta, complex plane.
Because it's the integral, because it seems to kind of jump if you cross real line here.
Yes, I'm crossing, yes.
C'est eta bar dans I transpose ou eta?
No, eta bar, yeah.
It's eta bar, and this is the complex conjugate, if you want, like that. Because I'm separating the integrals complex. Okay. No, what's happening here is that each of the integrals there, as function of eta, you know them. I mean, they are hypergeometric, right? So each integral, line integrals, have monodromies around eta equals 0 and eta equal 1. Okay. So in fact, I1 of eta, so there is an action of the monodromy. So if I call sigma to be 0 or 1, so the action of the monodromy on that vector here will give me a matrix that I call M of sigma. This is the monodromy matrix. Times I of eta, okay?
The matrix depends on signs of this ABC, yeah?
It depends on what?
It depends on these parameters ABC, yeah?
It depends on ABC, yes. Yeah, yes. It is, this is phases. There are phases on ABC. And you, well, okay. So now what's happening? So the statement, well, actually, it's a theorem, okay, theorem. If I look at the monodromy around sigma of the function g, a, b, c, a bar, b bar, c bar, eta, so I'm going to get, so here is the, I have the transpose, I have I call that I1, eta bar transpose, so I'm going to have the, so this has phases, so this is a complex value. So it's M sigma bar transpose G1 M sigma I1 eta. Okay, so this is, and now the statement is that G1 is such that so G1 is such that the function has no monodromy. So that means this quantity is the same matrix. So G1 is a diagonal matrix. In that case, in general, it's a block diagonal matrix. When I have n points on the Riemann sphere, when I have just 4 points, it's diagonal. And if you do the computation and you check with the, so the fact is that, so this is a fact. So that tells you that actually this function has no monodromies. Okay. Now the thing is that either then I could have said, oh, then I know my basis of integrals, and I don't know what is G1. And I want to compute it by imposing that I have no monodromies. That gives you conditions. You can solve them up to some constant. And so in the 4-point case, that determines up to an overall constant that you have to fix if you want to identify this with the physical string theory amplitude. But so that's a very powerful statement to us that you have no monodromies in 0 and 1. But you see, this is precisely where the things get interesting, because, yes?
Sorry, just to make sure. So G1 is that matrix over here in the middle.
Yes.
And
so there is
is this theorem true under the requirement that A, as you wrote before, that A minus A bar
is an integer? Yes, yes. I'm sorry. Yes, yeah, of course. If and only if A minus A bar is an integer, B minus B bar is an integer, C minus C bar is an integer. Okay.
For example, A bar is really the complex conjugate of A?
No. Well, tilde.
How do you get this? I mean, then I don't understand this second. I mean, the other in the board on the board just up.
What, you didn't understand what?
You have the A bar, B bar, and so on gone in the second line.
Where?
From the first line to the second line.
From the first line.
No, yeah.
To the second line.
So where have the bars A, B, and C gone?
That's a good point. Yes. Yes. Okay. So.
Because you said conjugate, I thought.
Yeah. So. Yes. The fact is that okay, I didn't give you some details, but the phases here they involved A minus A bar. So I use the fact that the difference is an integer, so that because of the sinus they give you some sign, and at the end of the day the sign disappears because you have A bar on the top and bottom, and you have okay. So there is a
this row vector, does it have A bars and B bars?
Yes. So this one is the same. The one is the same with everything bars.
Yeah,
Okay.
no, I think it's maybe because we have a really good configuration on exponents as well. One can assume that all numbers are real, yeah, but just avoid.
Yes. But you see, this vector is the vector composed by this integral, with you have a bar, b bar, c bar, eta bar, okay? And the difference between the variable and the barred variable is this is an integer. This is important to have no monodromies. No, they are not complex conjugates. I mean, it's just the fact that it's
No, I see. Yes, it's better really to think about them real because.
Yes, then you do everything.
It's still anyhow it's more.
Are you saying that it is enough to check this absence of monodromy for the product to prove that the original integral over dz bar is equal to this? Are you saying this is the proof?
No, this is a constructive proof. I mean, I don't have time to do it, but what you do is that you deform your integral by an epsilon. You move your contour of integration, and you have to be careful about the fact that okay. So here, when I split that integral, okay. Well, there is a formal proof, but there is a constructive proof as well. So here what I've done is that I have, for example, lifted the absolute value of 2a. I've written it's z bar a, okay? But the thing is that if z is a real number, that's fine. I mean, because a is supposed to be a complex number. So you have to make sense of the fact that you define the power correctly. If z is, for example, is a negative integer, a negative number, here you have a phase because you need to make. Okay, so maybe let me write x. If I have minus x, yeah, and I have to make sure that I define correctly the way I'm splitting this thing. Okay, minus x. So that I have a well-defined definition of the power, right? So what I'm doing is that you have to play with, when you look at this, you have to play the exponential to a log of z bar. And so when you split the log into the log z and log z bar, you have to use the determination of the log and to pay attention to the branch cut. So when you do this split, that you have to make sure that every quantity that is raised to a complex or real power is positive here. So that depends on the contour of integration you use. So this is why here I have everything that is positive inside, as long as eta is between 0 and 1. And here I have zeta between 0 and 1. So this is positive, this is positive, this is positive. Okay? So, well, so the fact that when you do that, then you get phases. And the phases are precisely the quantity that come here, and that will build this matrix when you do the holomorphic factorization. Okay. So now, what you do that, you use in a way the way you split the log z square, which is the closed string Green function, into the open string Green function that is the log z plus log z bar. And there's the bar of the complex conjugation. And the bar of the complex conjugation is precisely the one that comes into the monodromy computation and the cancellation of the monodromies. So this is a general statement. No, I'm lost in my. What do I want it to say? Ah, yes, I wanted to get this one. So this is a general statement. Okay, so yes. So this is a general statement that any integrals on the Riemann sphere is of the type, okay, so that I will write. So this is product S I n plus 2 d zi can be split on a linear combinations of, so it can be written as a vector. Okay, so do we have a color chunk? Yes. So what I want here, so this is the thing you get from string theory, that is the numbers. If you want to get the function, I have to put back the eta dependence that is here. So I'm going here to put, so this is the value. Let me write it like that. So this is the value at eta equal 1 of the integral that is of the type E1 to n d2 zi. So this factor doesn't change. Then this factor here doesn't change. Si n plus 1, etc. But here I have 1 minus z, and I have eta minus z. And here I will have something that is, let's call it bi, and then I will have something that is called ci. Okay. So I'm doing the same kind of deformation that I'm doing here, where I'm introducing an eta variable here that I'm splitting. I've decided that I split that term, where so that when eta equal 1, these two guys merge into that one, and then there is some relation between the b and the c. Okay. And what you can do is that you can even define, as I did it, with holomorphic and anti-holomorphic factors with a powers that are a and a bar or a tilde, b and b bar and b tilde, so that with the condition that actually the difference for the given monomial, the difference between the holomorphic powers and the anti-holomorphic powers is an integer. Okay, so this is, but to make it simple, this is the value at 1 of this integral, and this integral actually is, okay, I1, let's call it bar eta transpose g n I1 eta, where this object here, I1 eta, is a size, a rank. Well, it is a vector. It is a vector of, actually it's rank because all the components are independent under monodromies, of size n minus 2 factorial, composed of ordered integrals that are of the type here, that are given by essentially the same integral that you have here, where this time what I do is that I write x to make clear that I'm integrating over the real line, Sij, and then I have product 1 to n xi minus 2 alpha prime si n plus 1, and then I have the 1 minus xi to the bi, eta minus xi to the ci. But here I have to tell you that this is an ordered integral, so that means I have to order the integration variable between minus infinity and plus infinity. So that means I have here the real line, and I will have for example, I can have, suppose I can have x1 here, x2 here, x4 here, eta. So eta is not integrated over, but eta has to be somewhere. So let's make a dot for eta, and then I have, okay, and this is the real line, okay? So what's happening is that you have a class of integral where you have ordered the variable of integration around the real line. I've put the absolute value, but of course, if x1 is bigger than x2, when you integrate, it's the same as x2 minus x1, but you have to keep in mind that this is a complex power, so you have to pay attention to this. So there are well-defined quantities that are generalizing this hypergeometric type of integrals. And this function, of course, as you know, they are generalized hypergeometric function. They have monodromies. They have monodromies in 0, they have monodromies in 1, they have branch cut. Okay? But the quantity here is analytic on the complex plane minus 0, 1. It has no monodromies. And precisely the way you see that is by you have here the set of integrals that you can write that are independent with respect to the domain of integration, here a function of eta. You have here the other integral where you have and then you have a matrix in the middle that is such that it satisfies the property of the absence of monodromy that is over there. So that is a statement. Okay. So now, so this is a generic fact that at the end of the day implies the very special case that
these functions of eta without monodromies, they are meromorphic, they are entire, they are what?
So that it's a real analytic function. Okay. Yes. So Thibaut, I'm going to answer your question. Can I answer? In eta, yes. So, okay, so now this is what I'm going to tell you what are these functions. So in a sense, where is my blackboard? Right. Yes. So this object here, when I did the alpha prime expansion, gave me these integrals that are numbers, promoted them to function of z, okay, eta, and that gives you polylog, okay? Now what's going to happen is that the alpha prime expansion of this quantity is going to be a cousin of that one, but that will be the version of this polylog without the monodromies. Because, I mean, first, yeah, I don't know. You can, in your head, you can do it. I mean, in a sense, I mean, if you have this expression that I have on the blackboard and you expand both, you will get the polylog with the argument eta, the polylog with the argument eta bar, and then the coefficient in the middle is such that actually it kills the monodromy exactly the way Francis Brown explained how he makes it single valued. So in a sense, I mean, this is the way you see by an explicit computation without sophisticated approach, the single valued that you manipulate quantity that have no monodromies when you do this perturbative alpha prime expansion of the genus 0 amplitude. So if I go back to my genus 0 amplitude, this is what I want to show. Yeah, okay. Voila. Okay, so what you have is that you have an integral over the. I've succeeded in completely messing up my notes. Okay, very good. Ah, no, that's it. This is here. So if I look at an integral, the integral that is over the Riemann sphere of z square, okay, to the minus alpha prime s1 2 minus 1 minus z square to the minus alpha prime u minus 1. So if I do the alpha prime expansion, so I have to pay attention that the fact that I can have poles, so when I do alpha prime expansion, but if I look at the regular part, which should be the equivalent of that part, I'm getting a term, terms of the type integral PC1 the log of modulus z square to dn divided by factorial n times log of 1 minus z square factorial m to dm, and then d to z z modulus z square 1 minus modulus z square. Okay. So this is the equivalent of that integral, except that I have modulus z square everywhere, and instead of having interval between 0 and 1, I am on a Riemann sphere. Okay. So now what I do is that I do the same trick as before. Okay. So I first want to discuss the difference of this. So we have log of z as branch cut, and monodromy. So what no, I've made a mess of my notes. Yes, this is what I want. But the real part of log of z as the monodromies around z equals 0 is log z then log z plus 2 pi I, right? So if I take the real part of that, I have no monodromies, and this is the log of zz bar divided by 2. Okay? The same log of 1 minus z as monodromy around 1, but the real part of log of 1 minus z, which is 1/2 log of 1 minus z bar, has no monodromies, right? So in general, in fact, if you can define combinations of polylogs so that you don't have monodromies. Okay. So for example, if you take Li2 of z, which is sum n bigger than 1 n square z to the n, it has monodromies. But if you do Li2 of z, if you take the imaginary part of this, you add 1 minus log z log of modulus of z, and you call that d of z. It's analytic, and C except 0 point. It has no monodromies. So this is the Bloch-Wigner. So now, what happens here is that if you compute that integral, yeah, what you do is that either, at the end of the day, you get the version of that polylog that has just where you have. So what have you done here for the Li2 to kill the monodromy? You have the Li2, you added the complex conjugate minus the complex conjugate of Li2, and you have added some lower order polylogs so that you kill the monodromies that you get when you go around 1 for this quantity. So what's happening is that when you compute this, and you compute it the same way, so that means you introduce an eta variable. So you make an eta here, and you make an eta here. So this integral gives you, so let me call it QSV ij eta. So Q ij eta SV is the version of this Nielsen polylog Li 111 I plus 1 eta without monodromies. And one consequence of that is that if I find my notes, okay, here it is. One consequence of that is the following. Okay, so in fact, how do you want to do the computation of that integral? Either you build the single-valued polylog, the way Francis Brown has explained to us, and I'm not going to explain to this on purpose, because I want you can do it by hand. What you do is that you do an holomorphic factorization of that integral. You split the two integrations in z and z bar. So what you do is that you deform the contour of integration in z and z bar, and you pay attention to the fact that when you have the phase, you keep track of the relative phases, and you get a collection of integrals that you have to sum. And some of them, actually not some of them, but all of them actually will become of that type, because you see the poles here are the same. I mean, well, and this is logs. And at the end of the day, you are going to rebuild something that will have some polylog of eta bar, and then you will have quantity that will have lowest weight from one integral and compensating weight from the other integral. And at the end of the day, you will get something that as a function of eta will have no monodromies. So there is one class of integral that is one class of single-valued polylog that is of particular interest, and that will help me to end up with what I want to say genus 1.
So are the single-valued polylogs real function?
They are real function
of a complex variable.
Yes, they are real function of the complex variable. You see, I'm sorry. Yes, I had the real part of the log.
What real function can have a non-zero monod?
I have the real part of.
No, but it's locally finite sum of holomorphic times anti-holomorphic, and the property is altogether.
Yes, it's a real function. Yes. So I'm going to write an example of function. Okay, so what do I want to write? So I want to write something that actually is generalization of the Bloch-Wigner. So I want to write something that is dAb of eta, that is -1 to dA minus 1, sum k. So A is a positive integer, B is a positive integer, A plus B minus 1, so k minus 1, A minus 1, minus 2 log of eta modulus. Okay, I don't think, yes, okay, that's good. A plus B minus 1 minus k divided by A plus B minus 1 minus k factorial. Li k of eta. And then there's the same term with B, but you see kb A plus B plus minus 1, k minus 1, B minus 1, minus 2 log z, log eta, sorry, to the power A plus B minus 1 minus k. So everything looks very symmetrical. Minus 1 minus k factorial. But then here what I have is that I have Li k of eta bar. Okay?
So Pierre, just not to get lost, the final would include just one number, yeah? Integral property of log and powers of log and power of log 1 over z. Then introduce extra parameter to deal with.
So it's a function.
Yeah, you get a function, but at the end of the day, you have a related one and get some number, yeah?
Yes.
Yeah, which we didn't explain.
I'm going to tell you. I'm going to say it. Yes. So you get. So this is to explain to you, to show you an example of the way you get from objects that are multi-valued, you get quantity that is single-valued of a given weight. So this one is single-valued quantity. It has a branch cut. It has a branch cut for it starting, so 1 infinity, if A different B, and if A and if A equal B, it's analytic, real analytic. It's real analytic on C minus 0, 1. Okay? Very good. So now, if I look at what these functions are, so d11 of eta is minus 2 log of 1 minus eta square. d12 of eta is 2 times log of z, log of 1 minus z, eta, yes, plus 2I imaginary part of Li2 of eta, and d21 of eta is d12 of eta minus 4I d of eta, and I'm going to write another one as an example, d22 of eta.
I, you said?
I don't understand. What's the question?
You said I?
I. Where's I?
No, for what? What is the extra term? It's so small.
4 I d of eta, and d is the Bloch-Wigner.
Thought everything was real.
No. The Bloch-Wigner is real analytic. These functions are real analytic when A equal B, but when A is not equal to B, they have branch cut.
But they are not even locally analytic.
Complex valued real analytic, yeah.
Yes. That's
the initial holomorphic entity, holomorphic function, but
complex
not real.
valued real analytic operator.
Yeah, I have Li2 of z of eta minus 4 real part of Li3 of eta. Okay? Very good. So now you see that so this one is our closed string propagator on the genus 0. So you see these ones, I mean, as you pointed out, I mean, they are different from D. D is real analytic, and B is real analytic. Okay? But they have no monodromies, right? So now, if you do take the value at eta equal 1 of this function, you find that, okay, so take the Bloch-Wigner. If I take D of 1, D of 1, I'm getting zeta 2 here, I'm getting 0 from here. Zeta 2 is a real number, the imaginary part kills it. So D of 1 is 0. But if I look at D22 of 1, so I'm getting nothing from here because the log of 1 is 0. And Li2 gives you zeta 2, so this is zeta 2 times 0 is 0. But I'm getting something from Li3 of 1, which is zeta 3. So I'm getting minus 4 zeta 3. So the statement is, so I have to look in my note because otherwise. So DAB of 1 is 0 if A plus B is odd, and DAB of 1 is an integer, positive or negative integer, times zeta A plus B minus 1 if A plus B is even. Okay. Right. So now, now I'm getting to the place where I want to go. Because when I did the open string expansion, I was getting the Q's. Okay. It's gone. Yes, it's gone. It's here? No, it's gone. Whatever. So I had the integral, the Qij that were giving me all these multiple zeta values, the 1111n that Euler computed, and that give you the polynomial in single zeta values, but all weights. So you had zeta 2s, you had zeta 6, so for example. But in that case, here, you see here you have the Q, a version of Q that is the same Q as before, but this time where the kill monodrome is in the eta plane. And in fact, this guy is related to this one, the DABC. And when you evaluate this function at 1, you see that you only get, you see, A plus B is even. That means A plus B is odd. So you only get odd zeta values. So the fact that you take a function, you take a function like Li2 of Z that evaluates to zeta 2 of 1, you remove the monodromies, you make it single valued, then on the complex plane, then you remove, in that case you get a 0, so you remove the zeta 2. So in fact, the statement that people noticed by expanding a string Fourier amplitude in closed string, looking that they are missing numbers, they are missing all these even zetas, and there were very specific values of multiple zetas, is actually a consequence of the fact that any the string Fourier amplitude that are numbers are special value at eta equal 1 of a conformal correlator that can be expanded on conformal blocks this way. That is a single valued function of eta, and that the small alpha prime expansion of each of the multi-valued conformal blocks contains all the zeta values, and actually it's a theorem, right, Federico? It's a theorem that actually all the disk amplitude in string theory generates all possible multiple zeta values you can think of. They are generators. So all the ordered integral along the real line that you can write, they will generate all possible zeta values. And so this guy contains all possible zeta value number, but when you sandwich it, these guys with the appropriate matrix here that is such that this quantity has no monodromies, then you kill a subset of the zeta values and you project on a very specific subset that is the single valued, the value of the multiple polylog that have no monodromy, that is called single valued multiple zeta values. So this is a physics view of what is the relation, this single valued projection. And in fact, the claim is, so you see, the claim, yes, I will use that part that way. So to make it single value, I have to use a complex conjugation. Okay, I have to use the real part. I have to use Z and Z bar. So then I have genus 0. I have the involution. That means the sphere. And I go to genus 0 sphere. I get to the disk, for example. This is genus 0. So this is what I call the conform. So this is getting from the closed string to the open string. So the way in physics you do that is that here you do the conformal block expansion. Blocks. That means you write this quantity as bilinears in quantity that has here with appropriate conformal block coefficient. And this is the same as the single value map that is killing the monodromies. Okay? So in a sense, if you are familiar with what has been done in mathematics, in particular by Francis Brown, but this is the totally hands-on way of working out the single value map by doing the killing of the monodromies explicitly by splitting the Z and the Z bar integrals. Okay, so this is essentially what I could say at genus 0 in string theory.
Sorry, just so the GN there is the string KLT kernel, is it? on the left board at the top there. So that's the single valued map. Is the,
Yes.
That is the single valued map. And
It's a single value map, and this is the way you see that. This is the sine pi, except that. Okay, so right. On the blackboard, I had a matrix that was diagonal. So in general, when n it's block diagonal, the entries are not polynomial in the signs. I mean, they are rational function in the signs. So they have denominators. So if you want to have it in the form of KLT, where the coefficients are just polynomial in the signs, you have just to massage a little bit the integral that you want to use. So because you can change, you can use a basis of integral here, another basis of integral, and using the monodromies, that will remove the denominator. So in fact, but this is essentially KLT, or is the conformal block decomposition in the language of Dotsenko-Fateyev applied to the numbers, I mean, that you evaluate when you compute not a correlator function, but I mean an amplitude in string theory.
Well, here, sorry, I got lost. So do I understand that you say that if you consider this complex analog of this beta function, yeah, you get only polynomials in odd zeta value?
Yes.
And how you prove? Because it's, you mean this DAB evaluated one will be polynomial in odd zeta values?
So you prove it by computing that integral.
Yeah, and then maybe parameter, and then use this function. Okay, understand?
Yes.
And then this for these functions you know somehow that they're polynomials related to one zeta. So
I understand the question.
or is it some kind of like Euler formula?
No. Okay. So I mean, I will do it in a case where. Okay. So let me call n z to be log square to the n divided by factorial n. Okay. Let me call 1 z to be log 1 minus z m divided by factorial n. Okay. So now, if I have to introduce a notation, then okay. So if I look at an integral that is 0, a1, an, and then I want to introduce, suppose here, yes, z, suppose. Then the ordered integral that is 0, t1, t2, t, too many n's, z, okay. And then I look at dt1 over t1 minus a1, okay, wedge dt n tn over an. Okay, so it's an ordered integral. Okay, so you know it's a polylog, right? Grandeur polylog. So if I take the letters here to be just zeros and ones, okay. So So if I look at I 0, 1, 1, 1, 1, 1. Okay, so I need to have. So this is where I have a problem of. I think if I have in the notation that I had before J 1 and 0 I. This is Li 1, 1, 1, 1 J I plus 1, 1, 1, 1, 1, 1 Z. Okay? So this is the object that I discussed before. which comes from integrating 0 to 1 up to a factor that x factorial, I think 1 minus zx j plus factorial dx 1 minus zx, something like that, okay? So this thing up to some sign and that it's too late for me to fix. This thing is the thing I discussed with the open strings. It gives me the polylog, and it has this iterated integral representation, okay? So now I want to do the same. So now what's happening is that, as you know, in my hand.
Yeah, I really want to go because it's. I think you can interrupt. You want to go to elliptic.
No, but I just want to say that, in fact, what you do is that you do the same kind of integration as here. You write. You realize that actually this object is the version of that integral with the absolute value. So and then it has no monodromies, and so this is the evaluation of the zeta values that you have after you have killed the monodromies. But I mean, with the lack of time, I cannot do it now because I will have to do it's a one-line integration using the integration by parts, but it's too late to do that.
By the way, your starting example, G, the magnetic moment at zeta 2s, what would be the closed string analog of G without zeta 2s?
The 4-point function.
So physically, what is the the magnetic moment of the electron?
What is the magnetic moment of the electron in string theory?
The analog without zeta 2s, without zeta.
It's the closed string. It's the closed string amplitude. The fact that you have the closed string correlator, they don't have the zeta 2s in it because of this single value projection.
I understand, but physically, what is the physical analog of the magnetic moment of the electron, which does not have zeta 2s?
I'm not sure I understand. There's no analog that I know. I don't know any analog of that. Okay, so anyway, so the thing is that where was it? So I just want to conclude on the statement that okay, so the thing is that the property I discussed, I mean, about this single valueness, was to see that as a reciprocal of the involution you get when you go from the sphere to the disk, right? And the fact that conformal correlators are single-valued function of the extra variables, and that they are decomposed into your multi-valued conformal blocks. So this is a statement that exists to any genus. So genus 1, if instead of being a genus 0, here I have, instead of having z minus z bar, I have theta functions, for the prime form being on a torus, I have the same kind of decomposition. So I have decomposition of my genus 1 correlator on conformal blocks at genus 1 that are the open string amplitude at genus 1. So, and I know that, so the analytic property of the closed string amplitude on higher genera, I mean genus 1 or genus 2, will be again the same. It will be a single valued function of this extra point that I call eta. So, in a sense, this construction generalized to higher genus, if you can do it, gives you a way to build the equivalent of the generalization of the single value map from genus 0 to higher genera.
Actually, in high genus, you given for a given conformal structure in a curve, or you integrate over them?
No, I fix tau. I fix the conformal. You fix the conformal structure, fix tau, and you just integrate over the point on a given elliptic curve. Okay, so a fixed. So I don't have time to discuss that. So the thing is that this is the understanding of this map at higher genera is not so well understood yet. But the only thing is that this physically motivated construction, where actually you can, if you, it's just a computation you can try to do by splitting your integrals, I mean, gives you a way to construct the map when you go to higher order and have generalization of the function I described here. So in a sense, I mean, I can't really, because of lack of time, I can't really say more, but as well because the theory is less well understood beyond the genus zero case. So this is all I wanted to say. Thank you.
Encore des questions?
I have a very naive question. About the theorem you wrote. So, Taylor's quantity, so you have integrals here, so you split the holomorphic and the non-holomorphic part, but by construction it seems because you have only absolute value, but the exponents will be the same.
Yes, that's right. Okay. Yeah. So there is the, yes, you're right. Okay. This is, you have the same statement when, okay. So the theorem, because it's a theorem. So these guys are complex, right? But I can have as well anything that is a zi to the ni, z bar j to the n tilde ni, 1 minus zi, let's call it mi, 1 minus z bar m tilde I, as long as integers. Because what's going to happen is that you are going to look at monodromies near 0 and 1. So essentially you are going to produce phases that are two powers of pi times some integer that will be a combination of these guys. So this one will just be totally immaterial in your computation. So in a sense you have a class of integrals in general. In fact you need the generalization to that. But for the case where you have the complex object, I mean, here this physical parameters that are real or complex parameters, then you need that the power is the same for the holomorphic and anti-holomorphic. So this is if you want to have an integral that has z and z bar with a and b, a minus b has to be an integer.
S'il n'y a plus de questions pour l'instant, merci encore.